Good morning, everyone, and welcome to this year's Christmas Colloquium. When I invited Barry Sharpless to give this talk, he asked me, outside of the fact that the colloquium is going to be given in December, what's so special about it? And what's so special about it is the person introducing you is actually one of Santa's elves. And I know you've been introduced by some very, very famous people in the past, but this may be the first time someone from the North Pole like this. So I wish you all a Merry Christmas and Happy Holidays, and I hope all goes well for you this Christmas season. Barry Sharpless is our special guest today, and he's going to give a talk about something that he is very passionate about, and that's applied click chemistry from dyeing cotton to drug discovery. Barry Sharpless shared the 2001 Nobel Prize in Chemistry for his work on chirally catalyzed oxidation reactions. And that was the same year that NIST's and JILA's Eric Cornell and Carl Wyman shared the Nobel Prize in Physics. In fact, I told Barry earlier, many of us were gathered right here in the auditorium and watched that ceremony live from Stockholm. So we didn't realize it at the time, but we watched you walk across the stage at that time too. Incidentally, the other half of the prize in chemistry that year was for work on chirally catalyzed hydrogenation reactions, and that was shared by William Knowles of Monsanto Company and Ryoji Noyori of Nagoya University in Japan. Barry's work, the work that he was recognized for, makes it possible to synthesize molecules and materials basically with new properties. This has been especially useful, I would say, over the last 10 to 20 years in the pharmaceutical industry for developing new antibiotics, anti-inflammatory drugs, and heart medicines. Barry Sharpless grew up in Philadelphia, went to Friends Central High School in Haverford. And during his high school years, at times, his mind drifted into dreams. I'm taking this now from his autobiography, so he knows about this. He wrote it himself. And so, like most teenagers at the time, he had dreams, daydreams, but his dreams were a little bit different. No, they were not of chemistry. They were not of catalyzed reactions. They were of the ocean and what we called the shore. I'm from Philadelphia too, and in those days everybody wanted to go to the shore. Here it's the beach we go to, but we went to the shore. In fact, one of his great loves is the ocean. It's the rivers, the lakes. He's been an oarsman. He's worked in the summers on fishing boats in the Atlantic Ocean, and he just loves the sea. And it's still one of his passions. He went to college at Dartmouth College and started out actually as a pre-med major and got exposed to organic chemistry, I guess, his second year, and thought, oh, this is really much more interesting than that other stuff. And so he majored in chemistry. Went on to graduate school at Stanford University, where he got his PhD. He stayed on an extra year to do postdoc work there with J.P. Coleman, and he also went to Harvard University for another year of postdoc, this time with Conrad Bloch. He got into a tenure-track position at MIT and spent the next 20 years at MIT, except for a couple of years that he went back to Stanford University to renew some of his research there. Since 1990, he has been back at the ocean, really. Maybe that was even some motivation for moving back to the West Coast. He's at the Scripps Research Institute, where he is the Keck Professor of Chemistry and a member of the Skaggs Institute for Chemical Biology. Barry is best known for discovering 3 reactions which often have his name attached to them. These are the catalytic asymmetric epoxidation reaction, the dihydroxylation reaction, and the amino hydroxylation reaction. The Nobel citation talks about the epoxidation, the Sharpless epoxidation reaction, as follows. Many scientists have identified Sharpless's epoxidation, discovered in 1980, as the most important discovery in the field of synthesis over the past 20 years. At Scripps, he continues his really career-long search for useful new reactivity and general methods for selectively controlling chemical reactions. Click chemistry, he's been, as I said, passionately involved with since he started this research probably about 5 or 6 years ago. And this is you can hear about it today. It's a set of powerful selective reactions for rapidly synthesizing new compounds. And he says, told me by mail, he can hardly sleep. This is really such an exciting thing. Things are happening so quickly that as I picked him up at the hotel this morning, he was working on some of this stuff. So it's really become a passion. Obviously, he's won many awards and prizes. Became a National Academy of Science member in 1985. The King Faisal Prize for Science in 1995. The Benjamin Franklin Medal from the Franklin Institute in 2001. If any of you are from Philadelphia, you know your heart pounds when you go back to the Franklin Institute to actually be honored with the Franklin Medal. And then he got the Wolf Prize also in 2001. Just a quick story, because he probably won't tell this story, but when he was asked what was the most exciting moment in all of these awards and stuff, it wasn't the phone call from Stockholm. It was actually a phone call when he became a member of the Academy of Sciences. And the reason this was so exciting was that he was actually giving a lecture at a conference, an invited lecture, and the call was answered by his wife, who was, and his wife and children were at the conference as well, and she was in the hotel room. So the person on the phone said, you know, you really need to tell him right away. This is really, really tremendously exciting and quite an honor and all. So she finally said, okay, I'll do that. So the kids were little, so she had to grab the kids, and she went to the conference, and he was giving a lecture. And as he was giving a lecture, he saw her and the children come walking across the back of the room and became a little alarmed. So he actually stopped his lecture and said to his wife, yeah, is there anything wrong? So she must have shouted from back of the auditorium, well, nothing's wrong. We just came here to tell you you've been admitted as a member of the National Academy of Sciences. Of course, the whole place roared, I mean, with claps and everything. And this must have been actually a very, very touching moment for you. I hope you don't mind my sharing that story with the staff here. So without further ado, can you join me in welcoming Barry Sharpless?
Thank you, Bill. Really, it's been a pleasure. He's such a gentleman and fascinating fellow, and I should have recognized his Philadelphia accent. But that story is actually pretty close to the way it happened. The thing that really was amazing to me, and this is a sign of the times, I think, right? I had no idea George Busey, the late George Busey, my sort of Swiss professor, father in imaging, had nominated me for the National Academy. In other words, this came out of the blue. You know, today, I don't think many things come out of the blue like that anymore. Nobody, you know, he was a real gentleman, European style. He just got my secretary, told her, get me some data, and I nominated a couple, 5 years later, that doesn't happen very often. And George was a real gentleman. And so was Nelson Leonard, who just passed away. We don't seem to be replicating those people in our field. Okay, water is a big thing in my life, as you heard, and mostly salt water, actually, because I'm not really interested in things that don't have creatures. I'm looking for creatures. I gave up on macroscopic. I look for molecule creatures now. See, I don't take pictures anymore. I don't go fishing. I still like being near the ocean and walking, but I'm looking for creatures, something I don't know is there. That's the metaphor. Coelacanth. That's that article. It was an autobiography. It was just the thing I wrote for the Nobel thing. It wasn't. My wife wrote it, actually. She knows more about me than I do. She told me I was looking for my coelacanth. So it's called coelacanth in catalysis. Because, when we found the coelacanth in 1938, that was our generation. Everybody's going into the woods, thumbs up, we're going to find the Yeti, we're going to get dinosaurs. It was the Japanese, just like us. They love monster movies. And anyway, anything was possible. It seems the world is less optimistic these days. This is, we went to the Antarctic on this one trip to South America for a meeting, and that was in in 2004 with the family, and my son was taking pictures, and I just couldn't believe how many of these little krill, they're about this big, little shrimp-like things. I guess they're not good for us to eat with the shell on because they have a lot of fluoride in them, but it's a metaphor for how rich life is on this planet. Down there, in the summer, in the Antarctic summers, it's just massive amounts of food in the water. So the thing that really, I guess I went to Quaker school. My father was from a Quaker family, doing something useful. I always like George Hammond's old quote here. It says, "The most fundamental, lasting objective of synthesis is not production of compounds, but production of properties." There are just too many compounds. I mean, even little compounds, like could be drugs, 500 molecular weight or less, and just have the elements of drugs. There's estimated to be 10 to the 63 possible structures. And that's like, there are 10 to the visible universe is estimated to have 10 to the 80th Daltons, protons. So 10 to, there's not enough carbon to make one of every one of those little guys. We haven't made any, we'll never make any. It's impossible. We'd all have to make, I think, 10 to the 30th compounds today for 10 to the 30th years. Grandfathers, children, everybody, 6 billion of us. So we got a problem here. I'm telling you, I don't have any reverence for structure. All I care about is function. I have to know structure. Structure is trivial, though. I mean, you know, this is 2006. If you don't know the structure, you just tell somebody what you know and don't know. But the structure is not what we need in this world. We need the function. There are many ways to get function, I think. Connectivity is the way that chemistry, it's the metaphor for everything in chemistry, right? I mean, you got to get units that aren't connected, and that's the message. In life, that's the message. Cobble together proteins. It's pretty boring in a way, but it's 20 building blocks cobbled together, and that's the message. And that's the verb, also the verbs and the message, read off of the nucleic acids. So the connections, this is a great word because you see, it has a lot of things in it. It has everything we need. The Holy Trinity. Carbon, nitrogen, and oxygen. And so it's got 3 of those. I like that. And then it's got S, could be sulfur. And actually, Se is selenium. That's got me tenured at MIT. Titanium's in there, too. But this is the pyramid that I really saw coming on strong in the last few years. It's especially 3 nitrogens. Nature doesn't use more than 1 usually, but for her connections. And these we use sometimes, hydrazine-like things. But this is a magic place. I'll tell you more about it in a minute here. So if we have reactivity, that's what chemists should do. They should understand why reactions occur and how to get good reliable ones, I think. That's my belief. Because the structure, you can't get from one place to another in terms of new composition of matter unless you can understand reactivity. It's the structure, yeah, you might want a structure, but you got to know whether you can make it in a realistic sense, and that comes from understanding reactivity. And once you get the connections, you begin to have the chance for new properties and functions. That's the idea of click chemistry. So click chemistry is just a way of, it's nothing new. It was just, I had to go back to before 1950 to find all the good reactions. There wasn't anything after 1950. And I didn't invent any of these click reactions. They were there in the old German literature. You know, these guys didn't have chromatography, they didn't, but they were good at making compounds, and they took what they could get, and they crystallized out, and they made a lot of drugs that way. They're heterocycles. So it's like a few good men. You know, what can you do with a few good reactions? The Marines type of approach, and it's sort of a back to the future idea. In other words, if I don't use things that I can't really count on in a pinch, then what can I get out of that 10 years down the road? And I think you have to think down to the, back to the future. Polaroid. I loved Polaroid. It was right around the corner from MIT. Land was a genius. That was a wonderful thing. I'm sure you remember those things. Pull that thing out. Whoever thought that would go away? It's gone. Kodak, they're going to try, but hey, I don't give them much chance. Things change in this world. You can't have anything that, unfortunately, you can't have reverence for anything. You have to be ready. We do, as human beings, need reverence for life and a lot of stuff, but we just hang on to things too. When it comes to the technology and how you can make a living, I don't know if it's really able to have the kind of stability that we seem to need in our hearts. So I'm looking for a no-nonsense way to make things. And so what you'll notice about all this chemistry, it works best in water. In fact, I'm going to, because you guys are into the standards and basic things, I'm going to tell you something about water that I think is really amazing. It's not, we all know water's amazing, but these click reactions, as we did them over the last 5 to 10 years, we found out they don't only like water, the very best ones, by definition, work best floating on water. Now, this is like almost uncanny because life doesn't use click reactions. She wants reversible chemistry. We couldn't get off the ground if we couldn't recycle the parts. You know, we eat other organisms, they eat us, and we turn into what we need to turn into. And that, we wouldn't have a chance without modularity. But life is different than us, and we don't have much control. So I was looking for some really good reactions. Bang, they happen. But they happen in water, and that's great because that means you don't have to protect anything. You know, like life itself, you can sort out everything. If you're allowed to use water as a solvent, then you can't have interference from amides and hydroxyl groups. So here's the idea. You just, this was just pure water, heated for half an hour, and opens with buffered azide and nice crystals. These aren't explosive or anything. You can just burn them, but they just burn normally. And then you put them on water for an hour. They don't dissolve. That's an acetylene. And it goes click, and you got a nice solid. You just take the crunchy crystals off the top of the water. And what I like about click chemistry, we kept on going on this. You keep getting more material. You don't, you know, it's not, you don't have any chromatographies. We just don't allow chromatographies until the end. We have 3 LCMSs because everything is, and no NMRs. I hate NMR. I mean, NMR is great, but for mechanism, I don't need NMR. I got the structures. They're coming out the way the molecular weight tells you the structure, okay? And the retention time on the LC, you don't need anything else with this chemistry. Yeah, mass spec rules. And that's the paper that was, this is the manifesto, which I think came out much better than we thought. We didn't have anything. All we had was some ideas to use epoxides and use click chemistry, strain things that bang, but very selectively bang. That was the idea. And then, oh, this is for us, Philadelphia. 3 simple letters, but getting them assembled in the right order takes more than a good typesetter, even one of Benjamin Franklin's skill. Well, if you're a physicist, like a lot of you are here, you'll know that you know, you can have atoms in the gas phase. In deep space, you can have carbon atoms and nitrogen and oxygen, but you can't put them in bottles and arrange for them to meet each other one at a time. So it's a very sticky part of the periodic table. You know, there's no empty orbitals. Everything's engaged. There's just hardly, it's a real tough area. That's why it gives the stability to make life hang together. But it's not easy to put it together. And here's my quick course on stereochemistry. I've always liked this. The MIT students seem to like it back when I taught there. So this is the whole ball of wax here, right? We have a point. It's a carbon atom in deep space, in a high vacuum. I don't know if there's many of those out there. I don't think they can see those. They usually see things like cyclopropene carbene in deep spaces. That's the major species, one of them. Okay, so then we put a bunch of them together and we get a polyacetylene. Let's just stop at 1 unit. And that's the maximum state of unsaturation. That's a line. We then add hydrogens from across the plane, and we can do it 2 ways, but we get a plane. Then we add another pair of hydrogens, and now we're at the hydrocarbons, which we get out of the ground. and we usually crack them to get olefins. But these are, this is now like popping up into the three-dimensional world, and that's the way I used to teach how asymmetric, how you can get lots of stuff from olefins. You come through this evolution to the three-dimensional world. And if you look at the periodic, something about oxidation, I was telling Bill in his office just a few minutes ago that I first saw, my father was a surgeon, and we went to Philadelphia Medical Store, and there was this book on the biosynthesis of steroids. It was by Heffman and Mosetic, and they already knew enough to know. They had linosterol and cholesterol, and I only had high school chemistry, but I could see that 3 saturated methyl groups disappeared, and they went off as CO2. Boy, that really caught my, I just thought, and that's probably maybe the beginning of my interest in burning things and oxidizing things. So as you pull out hydrogens, that's equivalent to oxidation, you gain instabilities here. I'm just showing you the game here from phenylethane. You just go to styrene, and then you take out another pair of hydrogens, you're the maximum degree of unsaturation. I'm doing it here for diazonium ion, and down here, this would be a possibly made, but very unstable, tri-compound, but they're known, especially they're known if you have, well, that's a long story. Anyway, you start pulling hydrogens out of this, you get here, this is a known compound, triazines, especially when that's another group, R group, and then you go to the azide. So what we see here is the evolution of unsaturation growing in, and reactivity is coming in too. And when you have the atoms being the same in a structure like here and here, they're very, very unsaturated, very stressed compounds. Unsaturation almost by definition means reactivity, and yet they're really in a hole. There's about 25 ways to make azide. It may be up there, but it's in a hole up there, okay, a big hole. So all roads lead to azide in many parts of nitrogen chemistry. So that's kind of really something I think people didn't realize. It's that it's so stable in many ways, especially the aliphatic ones. But because they are made out of the same atoms, there's no big polar dipoles, and there's no big charge separations. And so they're really kind of not acid-base sensitive. They're stuck in a world that's highly endothermic, but it's kind of like a cage, and they have very few ways to go that they can get away from that unsaturation. That's the kind of paradox here. So they're cage tigers, and they only react, in a sense, they only react with each other. That's all they really know how to do. And even that reaction you're going to see is very demure, very, very demure, except for the ones that are activated, like the acetylene dicarboxylate. So we'll come to that. So here we have 2 entities, and not only are they highly stressed, but they're almost invisible in our world. They are invisible in acid-base world. That's what life practices, that's where we live. So this is the point that I'm trying to come to today, is the orthogonality point of this chemistry. That's what was a gift to us. We didn't expect it. We just ran into it. Huisken's cycle of addition of azides and alkynes, this goes back to the 50s. Actually, this was first discovered, this triazole formation, by Arthur Michael. He was at Tufts University. He went to Germany to learn. He did it in 1898 in Germany, this reaction. Of course, he probably didn't know. Well, he described the compound first, and it was definitely a triazole. And I thought that's kind of cool. He's the Michael reaction. And he was the first American that came back. He ended up at Harvard, I think, and had Germans coming over to postdoc with him. We all went to Germany in the old days. I mean, everybody went to Germany. It gives a mixture, and you have to heat it. That may be why there are almost no uses of Huisken's dipolar chemistry got used a lot, but not with azide as the dipole, with more reactive dipoles that were not orthogonal to the world. You can't use those in water and stuff. So I want to just start preparing you for what I'm going to imply here. This is a perfect reaction in a way that's funny. You'll see why in a minute. But the long reach of a perfect reaction, that's what I'm beginning to try to see as the main benefit of our quest here. And here's a case where whenever you have one of these reactions that's pericyclic, this is an ene reaction. So it's sort of like there's the alder and the Diels alder and then the alder ene. They're all concerted reactions. So here, this diazo carboxylate picks the proton off the allylic and rearranges. And this is an example from a few years ago what this reaction is like. If you mix these together, they float. Density 7.76 for pinene. And this one's heavier than water, but they float overall. So the color is from this, and you see it floating on water, and then you stir it. There should be a stir in there. And it transits down to the, and if you have more, stoichiometry wasn't right on this one. It was easy. It'll turn colorless, and it'll be 100% yield of this white compound, which happens to be heavier. So it transits through the water and ends up on the bottom, and that's not important. It could have started on the top and ended on the top, or vice versa. I guess that's not the point here. What is important to notice is this same reaction, if you do it neat, no salt, same thing, float those same liquids. Now, not as much because these are high boilers, and once you get started and things start warming up, then you can have an explosion, and it'll be a mess, but you won't, it doesn't mean it went faster. So we keep the temperature the same in a bath, and these two as liquids without water around take 70 times longer than with the water. That's this water effect. And they have to both be insoluble in water. If one is soluble, or if they're all in one phase with some co-solvent, it's not going to happen. What's going on here? Well, here's another one of it. Here, we did it on a 50 mils product, 50 mils, just stirring it. Each time I stopped, you see it going down. There, you just decant, pour it in a step funnel, decant, it's pure product. And it's very safe because this is a highly exothermic reaction, like all click reactions. But if you're going to do a dangerous reaction, can't get in trouble when you have water around. Well, I won't say can't, because some people get in trouble. There's ways to get in trouble, you know. Okay, now here, the best click reactions are simple fusions. And actually, you have to be a fusion to be a really perfect click reaction. And maybe you can see why if you think about it. It's almost like Bill Phillips was telling me, he made it very intuitive today for me to understand what you guys do, some of you. And I was impressed because I think it's really hard for me to understand physical principles, but I do have a molecule. I am a molecule. I think like a molecule. So I guess that gives, that's really true, unfortunately. That's maybe my secret. Anyway, this is the simple fusion. They proceed best floating on pure water. Now here's one. Went up to Edwards Air Force Base and got a couple half-gallon of quadricyclane. I don't know if you know what I've gotten into this high-energy community lately. It's jet fuel. Or actually, they have different things. It's not that great, I guess, but it does burn very well because it's got all this strain in it. And so they had considered it for fuel. But another thing it does that's really nice, you put it in the sun. See, it's norbornadiene that's been photolysed with visible light. You put that norbornadiene in the sun, and that's cheap out of gas. It comes as a cracking product. And it cyclizes, and then at night you run it over ruthenium, or you can run it over any kind of noble metal catalyst that gives up its energy. And you can run that cycle around and around. Anyway, the reason I wanted this was because it's been known from one of my old Dartmouth professors, Dave Lamal, that quadricyclane does a 2 + 2 + 2. It looks weird, right? But these bonds, this makes an addition here, that breaks, and you get a double bond there. It's a considered reaction in very unusual territory because of the immense strain. So if you do this reaction neat at 0 degrees, you mix these neat, no detectable products after 2 hours. But if you float this on ice water, which is, say, make sure you're at 0, It's done in an hour, and there's 100% yield of the product, which crystallizes on the bottom. If you do it in homogeneous phase, namely at a co-solvent, so these two are both soluble, it takes a long time, and it's always messier, too. That's the part. You may end up getting, sometimes the rates aren't that different when you do it without the water, but the product's always cleaner when the water's there. Every Diels-Alder reaction should be done floating on water. And that seems strange, but that's truth now, and I bet it's going to take a long time. Organic chemists hate water. We hate water. You can't imagine how much loathing we have for water and proteins and all these things, you know, in my generation. Here, floating the neat reaction of water provides 1,000-fold acceleration. Okay, now I'm going to, I know I'm probably not going to finish this lecture, but anyway, now we go to Rudy Marcus theory, and one of his postdocs. And Rudy's about 81. We went to China together last year, two cities, and poor Chinese host didn't get anything out of us because Rudy loved this on water thing. And we were just like, we couldn't get away from each other. My God, the guy is amazing. I mean, he's just like a kid. We had so much fun. Anyway, then he sends me a paper, and I've gone around to guys like Chandler, Burke, lots of smart physical chemists. They just look at this floating on water and they see, hey, macroscopic systems don't interest them, I guess, because they don't, I think there was something missing here in our understanding of water. It's not like the Breslow in water phenomenon, hydrophobic. It's nothing, it's not that, it's something else. So, and Engberts in Holland agreed, and he's the other great expert on water, and Rudy admires him. So Rudy sent me a paper about 3 weeks ago, a month ago, and I didn't read it right away because I was really busy with something else, and I just read it a week ago, and that's why I've got some slides. Rudy's in Taiwan now, but his student sent me these last night. And so here is this was an article by Engberts in Nature highlighting this on-water effect. So I'm going to give Bill these slides and a lot of other stuff in case you want to put it on your website and so people can have access to it. But here, this is another version of this stirring. Here we have this, this mix. Again, it's red because of the chromophore here, and then it stirring, and then it's over. And, and this is Rudy's slide, actually. And here, he takes the data from our paper. This is Sridhar. I'm not the first author here. Well, I mean, I guess the main author, but anyway, this is Rudy's slide. And here goes, you know, here are the rates like in toluene and homogeneous solvents, neat. So neat is 4.5 molar in this case, and it took 48 hours. Now on water, it's done at the same concentration, of course, because nothing's soluble. It's over in 10 minutes. And another solvent it's not soluble in, like deutero something, hexane, I guess, perfluorohexane. It's not that. It's not the heterogeneous aspect that's giving the rate acceleration. And then comes the homogeneous again, slow. And, but if it's heterogeneous and you have some methanol, it's still fast. So Rudy was trying to, I didn't understand what he was telling me so well in China. And then now I think I understand it better. And I'm just going to pass it. I have the paper. I'm sure he'd be glad if I share it with somebody if they'd like it. But what he did, I'll show you. This is an old observation. There's so many papers on water and what its structure are at the surface. And this is an oil-water story turned upside down because it's carbon tet. But this is apparently papers that described what they thought was going on. And mainly what happens with water at the surface is it ends up protruding naked hydrogens. It dangles hydrogens from its structures into the organic phase. So that's an energy cost there because these are naked in a sense, no hydrogen bond. And that's what Rudy, his genius here was to see that. I think he's really explained this to me, to my satisfaction. And I don't have enough slides to make it clear, but I get all these spectacular insights by Rudy because what he saw was that, okay, if I go back here, he saw that you could get with, it always gets the biggest rate accelerations when there are heteroatoms that are going to be in cycloaddition, okay? So you can hydrogen bond with these groups, and you don't have to pay for them. You see, if you're in water, you've got to break hydrogen bonds to make them to your thing. These are free. 2 or 3 free hydrogen bonds. That's the whole answer here. And of course, it's all fast as hell because it's at the interface, and it beats the homogeneous reaction. So you have to realize that the rates are enormous at the interface. Okay, so that's the way the story breaks down. And here you can see, what I loved about this, and if you're students or young, this is the kind of thing that a really good scientist does intuitively, I guess. And I'm a kineticist, a reactivity person. He said, okay, we got to get all these reactions in the same units. So he made, you make a lot of approximations. So he put them all in big equations, which I couldn't look at. They make me nervous. But they all came out, and he had these reciprocal seconds. They were all in that, They're very different reactions, but okay. Once you have that, then these were the experiments, the numbers that he got, that we had, and then his theory predicted that. He did theory, and so it's pretty good. You see, it's the basic fact of the what is it, acceleration here. It's very much faster on the surface. You see, very, very much slower without the surface. So that was good, and I love that. That somebody could come to a problem that I've been working on for 3 years, asking everybody I could think of, and they just. And I think it's a big part of what enzymes are getting, that extra kick. It's a big part of the extra kick from water. We know water does a lot of amazing things, but you have a lot of isolated water entities inside of a protein. And I think they're giving you a lot more than we know. Namely, imagine those free hydrogens dangling out that you can use. That's my message from Rudy. Okay, this is click chemistry in the old days. This is where we started. These are all hot things that will react. They're all from strained. We make these very strained things and we pop them open with nucleophiles. So that's the way click chemistry was until around 2001. And then all the others disappeared. And one day I was looking out across the Pacific, and the Terminator was coming from behind, and the sun was coming up over the Pacific. Bill knows I'm weird. I work at night. And I saw it. I looked out, I said, my God, this reaction is unbelievable. It's out in the orbit of the moon. It's not even an earthly reaction. It's invisible. Okay, it's not very fast, but it's so invisible that maybe I can use it inside of a protein. So I can use the protein as the reaction vessel. And so MG and I have always loved talking about crazy things. And we walked on the beach a couple of days, and we decided to commit a student, and we did it. And it took a long time because it was much more successful than we dreamed it would be, and it was almost impossible, actually, for us to measure femtomolar inhibitors. So anyway, back out to why you need this kind of type of property. No reactivity under terrestrial conditions. I mean, this is the ineluctable, as Joyce liked to say, ineluctable modality of the visible. And Morrison, I worship that man at MIT, powers of 10. And when we saw this for the first time from space, the NASA sent it back from some probe going out, then we didn't see any turtles, or there's no atlas down here holding it up, and there's a lot of water. It's blue. People say green. I don't like this green thing. I mean, the green thing gets abused a lot. People say they're doing green, but hey, this is a blue planet, Come on. It's going to turn green if we get a billion years, we get 100% more sun. We got to have, it's going to be cool. There's going to be all kinds of things growing through the ocean. It's going to have to be green. Okay, now, this is the mother of all azides. It's been just made in Germany by Bannert, and it's blue as hell, right? It is scary, but it's really amazing. All these do cycloadditions with acetylenes. That's a core. Not something I'm going to work with, though. Anyway, this is a glacier we got to walk on illegally because the young guys were in charge of the Zodiac I was on, and this is in Antarctica. Okay, I call it azides, and this thing's a little bit weak. I'm going to get my... Lerner's got 20 of these he bought that are wired to be 10 times more powerful, 50 amps or something. This is, I don't know. Lerner doesn't do anything on a small scale. Okay, this one's just a normal one. Could things get much worse? Well, what I mean by this, watch what I'm trying to say here. The Huisken cycloaddition, and Ralph Huisken saw this. When I came over there, I said, and I showed this lecture about this femtomolar inhibitor. He said, Barry, you got a problem. He's 86, sitting out there in the audience. And I said, what? He said, I can give you 20% of your rate acceleration from entropy, you know, holding things together. Where do you get the rest? And he was right. And so look at this. It's a very exergonic reaction, and it's about 70 kilocalories, but delta G, but I guess about 50 to 60 delta H. A lot of heat comes out. But it's very slow, and at micromolar concentration, now we're going to incubate the pieces with an enzyme. The enzyme's going to bind the two sides, and then they're going to hold together. It's going to go click. That's the idea. But it's micromolar concentration, right? Because we're dealing with an enzyme. At micromolar concentration, we measured the half-life of a typical saturated azide and saturated acetylene, and we backed off to room temperature from 100 degrees. And with an error of plus or minus 100 years, it's going to take 3,000 years to reach half-life. Well, I mean, if Ramses II in Egypt started this on the Nile, we'd be getting halfway there now. So that, you know, this is kind of like, I'm learning around here. Femtoseconds, everybody speaks atto-femto. Well, this is a long time, too. And so how can we possibly get anything good out of this? Well, that's what makes it so good. In retrospect, if it was, the more demure it is, the better, the more information you get when you see just a trace of product forming. And so Huisken's thing is the fittest click reaction because it's invisible, it's stealth chemistry, they're alien groups, they move invisibly through the terrestrial world that we live on the surface. So it enables, this orthogonal is a big word for me now, and it's actually a word that tracks in SciFinder, which doesn't have any math in it, so I don't know where you look up incidence of math things, but orthogonal is obviously used by mathematicians more, but it's coming up in chemistry every year since the 60s, and you know, when you put in one word in search, then you count the frequency, there's no years out of order. It's just coming up. We need orthogonal things because we're pretty blunt objects when you think about it. We're big, blunt objects. We're trying to do chemistry, we're trying to do a lot of things, and we need tricks. And so the idea was we used this enzyme, acetylcholinesterase, from an eel, and hijack it and use it to defeat itself. And this was the paper published, this cover from, this is that electric fish. He has a whole, like most of the electric fish, they have banks of acetylcholinesterase enzymes that produce these massive discharges. And so we're using the enzyme from Sigma and used it to incubate pieces and see if we could get a bond. And if you look at the, well, why would we want to do this? And I try to explain it already, but we wanted to do this by to use it, the enzyme to tell us something, to give us some whispers, some hints about what it likes. Because we always, before, chemists make a finished structure, they look at it, you know, they polish it off, and you know, they connect everything. And is it stable in water? And okay, good. We put it, then we just put it behind the veil, as it were, and ask, does this do it for you? And a lot of cold answers come back here. There's too many compounds there. Let the enzyme do the last step, okay? That's the idea. It's a pretty simple idea. And it turns out we got a Cinderella princess, or princess in the pea result. The thing didn't just whisper, it shouted at us because, anyway, it's a Trojan horse idea, but it's a little better than that because you just leave the pieces outside the city at night and they take them in and then they can't get out of their rooms in the morning. Everything's locked and you can run in and take over the city. This is a picture of the enzyme of the mouse with different, these are X-ray pictures from which things are removed. Either it's empty with water in there, but see this pseudopod here that's coming out? This is about 3 or 4 kilocalories up the energy surface of that enzyme. It's the sine qua non of this enzyme. It's a tryptophan 286. If it's not there, you don't have a cholinesterase. The serine at the bottom of this hole, and this one apparently guides the quat, choline in. And you're going to see that this one is what we discovered with this in situ that they didn't know existed, and they now think it's an important gating conformation for the protein. So we go fishing up and down the hole. This was known to bind on the outside. This is not a drug concept because that's monstrous thydium compound. But this was, Paul Merteller had shown this blocks the hole. This is the tacrin piece that had been a drug, binds down on the bottom. And so we went fishing with about, well, the permutations of these pieces. We put the acetylene sometimes on that. We put the azide on, different lengths. Obviously, some can't reach down into the gorge middle to make the bond. And these were the two that hit. Others, more sensitive machines later, 4 years later, we found other hits, but they're all exactly, always this piece, or you can also turn the thing around and put in acetylene here and azide coming down. But this was the major obvious hit in the beginning. And if I show you how we got the X-ray eventually, and so we're going to go into the gorge. We're going through the structure. This is this long gorge. It's full of aromatic amino acids. And here comes the tacrin labeled with an azide down. And this part is simulated to match an X-ray structure because tacrin has been X-rayed many times inside its place. So now we're sitting down here with tacrin binds. And here comes the alkyne down. And now you see them juxtaposed here. And it's going to snap together. Oh, it's too fast. Well, what I wanted to show you, and I don't have time to do half of what I think I should be doing today, so I'm sorry. I'll try to. No, I'll have to go on. We can come back to it. If we published this in PNAS when the X-ray came out, it took a few years to get the X-ray from Paul, team in Bourne and Marc Shaw and a husband-wife team in France, in Marseille. And this is the anti. What it turns out is the triazole normally goes this way and this way. The homo-lumo-controlled cycloaddition is more or less degenerate in this case. So it really can't pick between the two. So that's cool. I thought we're going to get some templating, If the enzyme is around this, it's going to go this way or this way, but not a mixture. And sure enough, we did get templating. We got only the syn. But the anti also forms, and it's a 500 femtomolar inhibitor, but it does nothing unusual. This is the way every X-ray structure had always been for the gorge mouth, whether it's empty or full. The tryptophan is in the wall, the tyrosine's in that wall. And so this is the anti, which the enzyme didn't make. Here's the syn. It ripped this out of the wall and changed a lot of other things, and it was now stacking on either side of the pi system of the ethidium. And the main thing is, if I pull out the inhibitors from the X-ray, you can see the holes are very different here. Even, down in, the serine's down over here behind that area. What I wanted to say was that when the inhibitor is in, see, what people don't get, of course, Weiskin did right away. You really need to be a physical chemist or physical organic chemist to understand reactivity. And Weiskin saw right away, well, this thing made this excursion. It's probably less than 1% in this conformation. Oops. This conformation is estimated to be 3 or 4 kilocalories up the energy surface. So, you're not going to see it by NMR. It's going to be less than 1% population. So what happened is these three things, one big molecule, 2 little ones, the azide and acetylene, they took a journey up the energy surface. And they got to this place they didn't know about. The enzyme certainly didn't know. It's a closet triazole synthesizer of the first magnitude. It does a great job of equalizing the dipole and everything, and it makes the triazole. But then it's stuck. So we call freeze frame. So you have the energy, you see. If you do things by equilibrium, you can't get much information out. But if you have a dart, you know, it's like that, what's his name? Oh, Muhammad Ali. Float like a butterfly, sting like a bee. Okay, this thing is so demure, but boy, once it goes, it's gone. It's gone. So you nail it. So we found this high energy conformation that way, and it's happened only. Oh, and then we went after the medfly is a problem, right? And also mosquitoes, and a couple other students who have left the group in academic jobs. They're going after the medfly and the mosquito with various selectivities, because all the vertebrates have this open, very similar, almost identical structure. All the insects, they diverged early, and everybody with a nervous system needs this enzyme, even a C. elegans. So it's everywhere in polycellular things. And the fly chooses to make this one out of these same pieces. And it's about 1,000 times difference in toxicity. One hopes to get something 1,000,000 times different, and then you could maybe use them as insecticides. And this is the fruit fly, which we got the enzyme from France too, from another group. Well, this approach has worked on 20 different proteins, some in industry, others that I know about, and I think it's really catching on. And I have a PET scan. I have a high throughput. It's become high throughput thanks to Hartmut Kohl, but in UCLA and at Siemens, and I could show some slides at the end about the PET scan, which is just unbelievable how that works. But this is just an HIV example. And see here, bindings doesn't have to be massive. This was a mutant protein that we're working on at Scripps, a mutant HIV protein and protease. Also, this woman is, Zana, is in Schimmel's lab, and they work on transfer RNA and RNA a lot, and this man is her husband in my lab, and they got a hit with the plasmodium the RNA piece, because this is for tryptophan, and tryptophan in mammals, I mean higher animals, is not edited beyond, it's such a weird amino acid, so evolution ablated the reading frame that tries to check if it has the right loading. So, but the plasmodium still has a checker frame, and they got a hit by, I'm not going to stop on this, but just to show you the range, it's a very hard targets when you're dealing with nucleotides, but they used a nucleotide with an acetylene and ran azides by it, and they got a selectively made selective inhibitor for that over this. That's human. This is the team. Palmer made it all possible, and Zoran. They can measure femtomolar, but even they gave up on attomolar, because we've since easily gotten attomolar inhibitors for acetylcholinesterase, and you just don't, you can't get them off anymore. It's like 26 kilocalories of binding energy, and so it's just no way you can measure that by modern methods, according to them. This is the guys who's Warren. He's the first student from MG, and there's my student now in England, postdoc at the time, and his father's he's the modeler. Poor guy. They model like crazy, but every time they modeled everything, they got a different structure, but then the enzyme structure comes in. Guess what? It's totally different, of course. Nobody could have guessed that. But the model, I don't have much. I love modeling for mechanism of small things, but not right now for those monster molecules. So I've gotten way. Oh, not good. Is it okay? Okay, I'm just gonna. I have to put this up. I usually put it up in reverse, because what's going to happen now? If I talked about copper first, I would have had everybody thinking there was copper now in that enzyme stuff. There's no copper. This is the pristine Huisken cycle addition. It's a very pathetic reaction in the sense of rate. But now what's going to happen, we're going to discover something almost the next day, thanks to serendipity. Because we needed now, we're getting these hits, we have to try to make syn or anti. We wanted to do that. So we started, I said, throw some copper in. Luke threw copper in. And from the very first moment, the copper accelerates the reaction over 100 million times. It may be 1 billion times. I don't know. There's so little of it active that we can't really get a handle on it totally. So here comes the copper. And it was, remember, this very slow reaction, and you have to heat it for 24 hours, 120 degrees to get decent, almost neat too, very concentrated. And you get the 1-to-1, and is it the strongest link? I mean, how could we like it, I mean, so much? Well, this is the serendipity of click chemistry. It started with the in situ idea, right? Because we were looking at simple chemistry from the old dark ages, and I noticed something about it. And then keeping things simple, that old KISS principle, gave us, suddenly ran head on into the, I mean, this works really better than we thought. Then comes, we got water. That water thing is interesting, I think. And then comes copper, and this is the final thing I'll talk about today. But this is mind-boggling reaction for the same for different reasons than what you might expect. I'll try to tell you a little bit about it, and then, well, there's many more things coming down this list now. This is the original trinity of breaks that came very quickly after the first idea here. And how much reactivity does a chemist need? This is like that Tolstoy short story, How Much Land Does a Man Need, which is one of my favorite. It's a morality tale writ large, and I recommend it if you haven't read it. But I think we need infinite reactivity, or we need more and more fancy. But no, I think what we need is something that's orthogonal. I mean, we need more and more orthogonal things, and you'll see, you've seen one reason for that. Let me show you some more. Barry Sharpless came in because he was a dyed-in-the-wool click chemist. He's an associate professor now at Scripps, and he's going to be independent for long. He and I said, my God, they won't. When Luke Green discovered the copper reaction, he was going back to England the next day, and he had it in organic solvents, and we tried to get it out. I tried to get the next fellow, Seva, who was a really good chemist, but wanted to stay in organic solvents. And Barry and I said, my God, this thing needs water, right? I mean, yeah. And so, so Valery went, put it in water, and he didn't even have to put copper in the right one form. It's got a copper oxide coat on it. So it recruits its own copper. It's stirring this acetylene, and then it starts once it gets started, it's just about 3 parts per million copper that did the reaction in the solution, and it crashes out. Now, I could tell you the mechanism of this. Let's see if I dare do this now. Let me exit a second. What's this going to come up? And I'll probably mess everything. Can I open that or not? This, if you're going to ask about the mechanism, I wanted to show you this. There are 2 coppers involved. We did the kinetics. One graduate student lived inside of a dry box. I didn't do this. This is all MG. Finn and Barry Sharpless. And so the kinetics, absolutely clear there are 2 coppers, and that's a critical point. But other than that, it's really hard to tell what's going on here, because the copper, it's so active when it's working, and we've got 2 more papers coming, they've got 2 more papers coming out on the calculations that are really proving beyond any doubt how good the calculations are now, DFT. But see, the azide, this isn't showing the whole thing. We have, this is the last part of it. You see where the reductive elimination occurs, and we definitely know it's not a cycloaddition directly, and this barrier keeps going down every time we find a new way to deal with the copper, the second copper. And I'll just go back. So it could, well, really we usually make the copper in situ. We use copper sulfate and ascorbate to reduce it, copper 1. And Valeri, about a week later, he went, he has a friend, a nurse over in the hospital. He got, this is not legal, right? But he got 10 cc's of his own serum blood and he centrifuged it. Thing goes better in serum, okay? This is strong inference. I gotta give you that article. I mean, in other words, some people might have taken 5 years to find out it works. Valeri is really good. And this guy has got strong inference. And he's a tremendous creative mind. And he also, when he smells ether, it's yellow, and ethyl acetate is blue. You got to have a little mixed up stuff, you know, to get any ideas. Okay. So then we go on. That was the first publication. And Seva and Luke and Valeri, and it's really Valeri's reaction, in my opinion, in the sense of showing how robust it is. And I'll just this is Valeri Fokin, and MG is the father with me of this in situ idea, and Hartmut has been off and on in my group for so many years, and he's coming back to Scripps with an adjunct appointment, but he's the CSO of a startup company, the PET scan thing, and we're the clicked amigos. And this is Valeri's graduate student here. No, I'm sorry. But Valeri was in China, and because one of my students, Peng Wu, is a famous, his grandfather's a famous teacher in the town where the bears come from, the polar bears. So any one of us who goes there apparently has privileges to go into the secret area in the back. And so there's 30 bears back there, and they're all looking like they're not on the evolutionary survival rungs here. How the hell these things ever lasted when man came around, I don't know. So, okay, then just to make sure copper was okay, I had to go to South America to visit this mine in the desert, and that's copper sulfate coming out of a leaching process. It's been 20 years it's been running out, and they take it and electrolyze it. Oh, I wish I could show you that. I couldn't find the right slides last night. But they get huge, beautiful plates. It looks like artwork. And so they take the copper sulfate, and 20 more years it'll run out, and then they'll go to another location. And that's Victor Martin. He's number 2, man. He's like one of the godfathers of the asymmetric oxidation. He and Katsuki are bosom buddies, and he's in Canary Islands now. Okay, gold, this is Kipling. Gold is for the mistress, silver is for the maid, copper is for the craftsman, or the chemist maybe, cunning at his trade. But said the baron sitting in the hall, iron, cold iron is master of them all. And I love that poem. But let me show you some copper. I brought it here because we get these in 300-pound buckets, and I'm running low now, so I have to get some more. But since you're the national standard something or another, you got to tell me. These are electrolysis anode copper balls. You just throw them into your plating. That's you just dumping them in. And this is supposed to be, I forget. There's 3 different sizes, and this is an exact number of moles. But I just wondered if you have any balances around it. Of course, we could weigh them on, but actually, I think I'll just pass them around. But look how beautiful the crystals are. See, they just pour it into a little sphere thing, and the crystal's unbelievably nice to look at. Yeah. Anyway, people, I give them out to friends and anybody wants them because they make great paperweights, and it's very pretty metal for its price. Okay, I think I better get. And then since I'm impatient, and we got this reaction, it was a couple of weeks later, I said, let's glue something together. So this is 2 1-inch copper plates with about 70 kilos hanging on here, and it's been glued. See, this is the glue. It's going to be a polymer made by the copper itself. If you have steel, it's still water the next day. But if you have copper, it's going to make this nice glue. And it's still very clear. The metal's very clean. I was thinking somebody in the Navy should be interested in this, because I had to paint a lot of copper on boats as a kid, and they really make a mess out. I was just thinking maybe this would be a good way to cover boat bottoms. This is the way we did it first time. We took this, we have about half a kilo of it. It's very stable and easy to make, and it's almost impossible to stop alkylating ammonia, so you easily get to try. And you put those together and just let them stand overnight or heat them for 30 seconds at 50 degrees, and you've got a permanent bond between the copper. And there's a couple more papers on this if you're interested in material science things. And so here we have this reaction, 26 kilocalories, right on the money, calculated or measured for the cycloaddition over Mount Concerted, okay? You've got 26,000 foot peak, and with the enzyme hugging it, it's brought down on the order of weeks, maybe a year. It doesn't really get as far as you think, because all you have to do is see that little blip in the LCMS. You're only making 1/10 of 1% when you can see it. So it's going to take almost a year still to finish, but if your enzyme doesn't rot. And but down here, this thing is just something else. And I'll just, it makes dendrimers, and there's my students who worked on that. We were in Kyoto, Japan, a couple years ago. They were giving talks. And it works inside of an animal. I mean, inside of a cell it even works, because there's copper in there, but that's something I can't tell you too much about today. But Ben Cravat is making lots of proteasome work. And you go in with an alkylating agent, and he went in to specifically hit a brain protein, sacrificed the rat, has an acetylene hanging out, which is very low tech and not going to cause any trouble. And then he takes the proteasome, puts the azides and copper in, and attacks the fluorescent agent and runs the electrophoresis, and you can see it picks it up. It can find a needle inside of a needle in a haystack. There's no way it's not going to go, and it's quantitative reaction all the time. It's like a polymer grade reaction, right? You can't make polymers. It's nothing new to the polymer world, but this is different than a polymer of the normal kind, because you can have anything hanging on it. No functional group will stop it. Phosphines, thiols. It goes from pH 2 to pH. Let's see if I can get well, Coleman's done a lot of, I'm going to give you these slides so you don't, the hydrogels, it makes great hydrogels. Hawker is one of my heroes in this area of material science, and he's done some beautiful stuff. Coleman's making, putting things on narrow, nano wires. It attaches things to viruses. This put on 60 things onto a virus, and people are really happy with it because it doesn't have any times when it won't work. So why did I say alien? Well, it's alien because the pH doesn't matter. I mean, you can go from pH 2 to pH 14. Temperature doesn't matter. You can go from -20 to 300 or whatever. But a lot of reactions would probably do that. But does it always give 100% yield? No. The reason nothing happens, the guys are like true love weights, you know. These guys, they don't decompose, they don't do anything until they react with each other. It's uncanny. No functional group. We've done reactions, 40 linear steps, 96% yield overall. That's what MG has done. Now here's something I wanted to mention, because Chris, well, you must have some use for this. I was thinking of patenting this because we got a couple liters of this solvent. This is the parent triazole. I thought, no, there's never been much around, but they're now making tazobactam, a beta-lactamase inhibitor with it, and it's starting to become available. And there's no reason why it couldn't be reasonably available. And people always thought when they saw triazoles, the guys in pharma, Novartis and Merck, oh, it's going to blow up, you know, the triazole. Well, the triazoles are bloody stable. Benzotriazole is much more stable than naphthalene. But look at this. Here's the DSC. You come out with this. It's a liquid at room temperature, 23-degree melting point. It tastes sweet. Crickets love it, and they go crazy for a day, and then they die. I mean, you know, things like that. I'm sorry. You can do that kind of thing because they're going to be fed. You go to the store and buy crickets. But other mammals don't like it too much. We injected it into some mice, and I'll tell you if you want to know what happens. Here is the endotherm. Big heat capacity, much bigger than water. about 200 degrees where it boils. It boils at 203. So I figure maybe you can use it for a heat exchange, right? A heat exchanger. It stabilizes copper, it stabilizes metal surfaces, so it probably would just be great inside of it, contained heat conducting transfer system. And DSC the measurement was stopped by Novartis at 300, nothing. And then if you go to the microwave, oh, I didn't add the microwave, I guess. Oh yeah, I did. Here's pure water over here at 210 degrees, 20 bar plus autogenous pressure. It's between 0 and 1 atmosphere at 210. I don't know why it's above its boiling point, but you see this increase in the mole fraction. This is pure triazole, and this is pure water. So it goes up much faster than water. It goes up like a linear bullet to the 200-degree mark in the microwave. So I think this compound, and it dissolves proteins. You can heat the proteins in it. They denature, but they don't crash out. It's weird stuff. Cytochrome C, it dissolves in it without losing any of its copper or its iron. I think it's interesting. And I guess, what was the other thing? Oh, and then I found recently at Georgia, this is interesting because I know you people like, well, fuel cells are going to have some get better and better in this world. And if you take polyvinyl triazole and polyvinyl imidazole, this is a very redox, much more sensitive than this. So Zhao and his colleagues made polymers of these, and this is 100,000 times more conducting with a little acid in it than the imidazole. And the reason is it's a growth, for imidazole to transmit, it has to turn over. Triazole doesn't. It can use a slippage to the 2 nitrogen, and they figure that must be the reason. Okay, it's alien, it's orthogonal, it's finished. There's the high tolerance of click chemistry. This is from Craig's lab. He's from Australia, and tolerance means you can not an alcoholic, I guess, but she's not. She's an undergraduate at Stanford, was working in his lab. Craig's now an academic at Santa Cruz, and I can't say enough good things about him. You'll love him if you get him out here for a lecture. And there's my coworkers, and I'm overtime. I tried to mention them anyway as I went along. So that's it. Thank you. Thanks.
Well, thank you, Barry. I think you took us on a journey there from so that we might understand a lot of the things that you're so excited about. Let me open the session today for questions from people. Got some chemists out there. Yes, sir. Right in the middle. Yeah.
Does the Scripps activated reaction also take place rapidly in
We're connected to Boulder too. So if you could shortly repeat the question so they can hear us in Boulder.
Okay. So my cells, actually. It would. You got to remember, see, the simplest the azides and acetylenes are slow, but you can activate, you put some electron withdrawing groups on the acetylene, and you can raise the reactivity quite a bit. You saw the diethyl carboxylate reacts it quickly. So yeah, in a biological system, you can't afford to do that because glutathione is millimolar inside the cytoplasm, and it's a good nucleophile, so we do a Michael addition. But yeah, well, Chris was showing me today how he drills holes in the sides of, I mean, I could see a lot of cases where you could suture your assembled vesicle together with the reaction, especially if you had copper in there too, right? And you wouldn't have any problem with that. I guess you could have a little copper, couldn't you? But I don't know whether you want it you want the vesicle to have a rigid structure or not. Is that what you're asking?
Well, actually, I was interested in the use of micellar chemistry.
Oh, that's a good question.
Micelles would seem to be a very good reactive medium, and indeed, this type of studies could explain a lot of what's happening in micelles.
Okay, now what happens is we did a lot of the tests, those tests you do, like add the guanidinium, You add a micelle to the water phenomenon, and you kill it. Yeah. You take it down. Yeah. It's not good. Because you see, it makes sense that it's not good. Because, well, it's, I guess, maybe Marcus and Engelberts would explain more, but it's different. This thing, the water phenomenon, of course, is just a totally different story in a way, but yeah. The cycle of addition is very slow unless you have the copper or unless you, we're not making any, see, if I had an enzyme like this and I put the pieces in, it's going to take a year to make it show up as an inhibitor because there's nothing there. It's taking so long to make it. But it's the power of analytical chemistry today. You only need a little tiny blip. I could show you on the PET scans, or Hartmut-Kolbe has now got this in microfluidics where you can do 200 enzymes at a time, and it all gets mixed and put into chambers. You shoot it on the LCMS and get the same result as you do in little Eppendorf tubes. And then he puts fluorine 18 on and shoots it into the rat, gets real-time pharmacokinetics. He sees the whole thing light up where it's supposed to, and sometimes it's really available in the cells I was telling you about, but it's like a COX-2 inhibitor. It goes in the cell, stops prostaglandin E2. It looks like it's going to be active. You shoot it in the rat, it never gets by the liver's first pass. It's in the common bile duct in 20 seconds. You need to know these things. People, I mean, Hartmut's doing this. He gets all the inhibitors down to nanomolar or pico. He shoots it, puts together fluorine 18. It's a go or no go in 6 weeks. And that's why I like this stuff. I want to give you that tape. Anybody who wants the PET scan stuff from Kolbe, it's got movies in it, and it's all about cancer. They started off with cancer diagnosis, but it's a drug discovery. It's a radical new drug discovery method, really.
I have a question, too.
Yeah.
Can you say anything about the connection of the click chemistry to the combinatorial methods that are so prominent in the drug industry? I mean, how does this fit right into that?
Yeah, well, what I find, there's the reality of what they do in big pharma is they love numbers and they get ready and they screen for 3 months and they can't stand false positives. I could show you half a dozen case studies where we just made one plate and we made the thing, so little copper involved, we made it right in the aqueous DMSO, and it was against the Foucault, the last step in Lewis X synthesis, or in other words, glycosylase inhibitor, and nobody knows why they work, but we got one that was 400 times more potent on the first plate. Now, if I have another azide or an acetylene left on it, I go down. But I don't go down for long if the thing goes through the rat and doesn't make it, you know, I throw it away. I just go take another one. They don't do it. See, in pharma, they got all these, they're too intentional. And there's no diversity in the goddamn molecules. Excuse me, but they're made, they're going for numbers, so that just the connectivity makes a difference, right? That 10 to the 63, you start to realize we're in one universe. Hartmut has a slide where he shows, we got this one universe. Then we have the Hubble Space Telescope view, and we've never even been in these other universes, and they're all possibly pharmacophore containing. They don't have any reason not to. It's just that it's not our world so far because we connect things. It's devil's in the details. Yeah.
Any questions?
Yes?
Okay.
Oh,
Terry?
When you started out, you were mentioning about life was not this kind of reaction because you don't want to have, you want to be able to go between different, not be in equilibrium, but go between different states rather readily. So it's energetically kind of ambivalent. These reactions look like they're energetically very strong in one direction. Would you comment on whether we don't seem to know how we got into the type of chemistry of life that we have now, because there don't appear to be a lot of intermediate steps. Would you think that these kind of very strong reactions might have at least led to the building blocks that we have around?
I don't think so. I think life always was facing water as the main theme, and in the beginning it was She was dumping her electrons into sulfur, not into oxygen, mainly, or into iron or something. But she did need that energy. She needed to have something to push things. But she, the reversibility really strikes me. Whatever was before life, and that would be before RNA, before anything. I mean, RNA. There had to be some, in my way of looking, there had to be something building up there. Unless the Orgel thinks it happened on a deep ocean trench on a rock. And Arrhenius, Gustav Arrhenius, I mean, the rocks have, you know, you don't need the membrane right away, maybe if you have a rock. And maybe we're all related to the same rock. I don't know.
Life formed on a rock. Any other questions? Yes?
Why copper? Why not silver?
Oh, good question.
So the question is why
It's amazing.
copper? Is that what?
Yes.
Why copper and not silver or gold?
I don't know. I was trying to think of some metaphor of this copper thing because
Back
it's
to
so.
Kipling. Back to,
Oh, what?
back to Kipling.
Yeah, back to Kipling.
Right.
Yeah. But silver, you can make the silver acetylide and they're stable. It sits there. Nothing happens. I mean, I've been explained by my friends who are real heavy-duty organometallic chemists. The copper's got its d orbital. It's a very simple element. You know, once you get the copper 1, it's got that acetylide. It's going through the copper acetylide. I don't know if I didn't show that properly, but and that's basically taken care of everything it needs because now it's not a filled shell, but it's D10, and silver's d orbitals that can come out. See, this d orbitals have to come out and engage in a funny way to make an alkylidine intermediate, and they're just much more stable. Silver and gold. You can make the acetylides, but the d orbitals aren't in play where they have to be. And the exchange of rate of exchange of things on copper, that's these ligands that are around, I bet you there's nothing, everything gets shed, I think, because we need ligands sometimes to stabilize in the biological fluids, but that's just a place where the copper hides when it needs to not become to copper 2. I think it has to get out of there, and it's just the it's a diacetylene dicopper complex, and the exchange rates of water on this are almost the same as on sodium, diffusion controlled. Copper is slippery as hell. I mean, if I measured copper in some part of your finger, I'd know occupancy of everything in your body. It's an equilibrium. In the old days, for bacteria, when the sulfur was around, one thing that'll stop it is sulfur and cyanide. Not permanently, but it'll just make insoluble copper sulfide. So there are carrier proteins for copper, but they're left over from evolution when the Earth was anoxic. That's my opinion. But O'Halloran, Northwestern, has shown copper is at equal. It's a pool, and you can't keep it anywhere. It goes everywhere. Does that help? That helps when you're slippery. I mean, catalysis really requires slipperiness. I learned that from osmium. Osmium, you'll never hold on to that element. And I don't have any plans. I'm trying to make a house so they can have copper stay where it's supposed to and inject it in the veins and it go around and feed strips of azide and acetylene in. It'll chop off plaque or something, a little motor. But you know, I don't know how to contain copper. I just don't think we can do it. Not right now, I don't know how. And maybe it's like that song, what was it? The answer, no, it's another thing. No, that's my answer to you.
Okay, if that's the last question, let's thank Dr. Sharpless again for coming.
Thank you. Thank you. You're